Okay, I was thinking that this is probably the first time that all five of us have ever been under the same roof at one time, even including AMS and AGU meetings. So you have the ability here to have any question on modeling whatsoever. And undoubtedly, two or three of us may likely be able to provide the answer. So we'll open up the floor now to questions. Can be directed generally to the panel or to anybody specifically. Yes?
Yeah, on the climate shifts, is methane hydrate release in that? What are you doing with that?
Yeah, methane hydrates is one hypothesis, and this is the clathrate gun hypothesis of Jim Kennett. And the idea is that there's a lot of hydrates stored in the ocean sediment along the continental shelf, and that if you warm the ocean a little bit, that can disassociate that methane and release it into the atmosphere. So it's kind of a positive feedback, right? So once you release that methane, it warms up the climate, and then it releases more of the methane. So the methane, the methane it's from plant life or animal life. Well, it's generated by life, and there's different processes that you generate the methane, and each of those has a type of signature that's that you can tell whether it's from ancient type of plant life or more modern, or like methane generated from peat bogs. So the type of methane that is there is not from ocean sediment.
Okay. Yes?
Can you guys tell us something about the hurricanes, like in terms of climate and weather, long-term, short-term? And there's some people saying that more severe events are occurring more often of late than they occurred in the past.
Okay. The current consensus about what hurricanes will do in the future is based on models. We can't say that much about what hurricanes will do based on data. And certainly for hurricanes in the Atlantic, the belief is as the climate warms, counterintuitively, there'll be actually fewer hurricanes overall. The number will most likely go down, but the number of intense hurricanes will most likely go up. So if you think of the probability distribution function, it's going to decrease overall in size, but it's going to shift to the side of the increasing intensity. So the tail is most likely to go up. So if there are landfalling hurricanes, you might get more Category 4, Category 5. But the overall number is expected to go down based on model simulation, in part because the conditions that generate cyclones are likely to be fewer. But in general, the atmosphere is going to have more moisture. As the world gets warmer, there's more moisture in the atmosphere, so there can be much stronger hurricane, and that's why the more intense hurricanes may increase in number. That's the consensus at this moment. I don't recall the global predictions, but global predictions are somewhat more stable than the Atlantic predictions. The global numbers may not change as much as the Atlantic. But again, it is counterintuitive. You think warm temperatures, more moisture, more hurricanes. That's not true. It's just few more intense hurricanes, but overall fewer hurricanes.
Yes.
This is excuse me. This is for Charles Jackson. I missed what were the known forces that caused the warm medieval period and the Little Ice Age?
Yeah, so solar variability is fairly minor in this. I think the bigger forcing is the volcanic one. So the warming is in some sense caused by fewer volcanoes and the cooling by more volcanoes. It's not so obvious in that time series, in part because what's happening is there's a lot of missing information there. One is that you could have a series of smaller scale events, but more of them that kind of keeps climate. When you have a volcanic event, you put sulfate aerosols in the atmosphere, and that reflects sunlight. So that's where the cooling comes from. But you have to think about the flywheel, and those being pistons, and that the ocean remembering kind of what happened before and integrating over time the collective net forcing from those kind of spikes.
So follow up, what's the forecast for volcanic activity?
Yeah, there is no forecast for volcanic activity.
No, no, it will continue.
Yes, it will continue.
Yes. Yeah, in the front.
You were talking about one of your last slides showing the aerial extent of the effective precipitation during that Heinrich 1 event, and your conclusion was that the tropics would have dried out. Would that infer that the tropical rainforest band across the planet would have died off pretty much?
So, I mean, that's the type of thing that is indicating this massive drought, is if they look at the pollen, and I think usually what that means is that the plant species really radically changes. And these things last a long time, so.
Yeah, because I was wondering then, because of the fact, or it seems to me, that plant life is one of the reasons why we have an atmosphere mix that we do now, with oxygen, nitrogen, CO2, killing off a lot of vegetation, you get increasing CO2, decreasing oxygen, and that should be pretty noticeable, I would think, from the geological record.
So yes, CO2 does vary a little bit during this time. So there is some amount of it. The main part of the way carbon changes in the climate system is through exchange with the ocean. If you look at the methane record, going back to the methane hypothesis, one thing that was very obvious from the ice cores, there were about 50% variations in atmospheric methane, huge. And so if you look at that kind of drought, that's, if you will, there's much less methane being produced on the land surface. So that kind of reinforces that. But the greenhouse effect from methane, so in this case, when it was cold, methane was decreased. So it's a positive feedback in this case. But when they do these experiments, it doesn't account for the scale, the temperature change that is associated with that. So it's a good, it is a feedback. It is positive, but it doesn't account for what we need to.
Let me comment. One thing to be aware of is that the vegetation is also strongly sensitive to how much CO2 is in the atmosphere. So during the last ice age, CO2 dropped down to 200 parts per million. Now it's 400. And that was probably not enough to maintain tropical forests. So people have interpreted the lack of tropical forest during the last ice age as a drought, but it could very well have been largely due to the low CO2. I'm not sure how well that's sorted out yet.
Yeah.
The medieval warm period was a period of warm times when there were not much ice extent on Earth, and the ice age, little ice age, was a time when it was cold and there was a lot of ice on Earth. How can you know that the ice extent difference didn't cause the temperature difference?
Well, it's a good good question. So, yeah, so when it's colder, your ice will expand, and then that will reflect more light. So that's considered a positive feedback. And so I don't think, so one of the changes that in those experiments is land is that L. And actually, I don't think we know, I doubt they inserted changes in glaciers in there. So either, what does that mean? So that probably means that your hypothesis probably needs to be explored further. But for some reason, the people who ran these experiments either didn't have the data to explore that idea, or they somehow just dismissed it. But you know, I guess usually what happens, you do a back of the envelope calculation. You think about how much of the expanded area is there for the ice, and you think about how much of the temperature change can that account for. Should we be including that in these experiments? And they may have done so. I actually don't know. That's actually not the type of experiments that I do. I do more of the abrupt climate change type of experiments. But it's a good question. It's a very good comment.
So you do the experiments that aren't successful.
Yeah, I like the failures.
Yeah.
How important are CO2 and methane in the models? how dramatically, if you look at the models, are they important drivers and factors in your modeling, or are they less important relative to the other factors that you're looking at?
So the well-mixed greenhouse gases are a dominant forcing for paleoclimate. In order to explain ice age climate and climate over millions of years, you need to know something about the amount of carbon dioxide in the atmosphere. But it's one of those things that it's a very good predictor of climate, but it's not everything, right? There's a lot of other, as you could see from the Greenland record, a lot of those variations did not involve carbon dioxide. So I probably didn't answer your question fully, but it's one of those things that we view as being a very important factor.
Yes.
They reported today that they're starting to detect minute, I think it's cesium-134 off California, and that it's coming over on the Pacific gyro. Is the El Nino or the La Nina going to affect that circulation at all, and maybe dissipating it sooner or bringing it quicker in higher quantities? Would that have any effect on the ocean itself?
Offhand, I don't know the answer to the question. I think more of how it's going to affect land. But what happened, I talked about those waves that propagate out from the Pacific. The waves have signatures in the surface winds. But those signatures are probably smaller than the mean ocean circulation that's there. So I suspect the advection of those traces will be mostly by the mean circulation rather than by these waves which are superimposed on top of the mean. So I don't think it'll change the overall flow that much.
Yes. Yeah, in blue shirt.
That's me. Thank you. This question probably goes to Eastbound on the data assimilation. I saw your slide. It was about 0.6% of data that's actually observed is assimilated into the models. So what is academia and research organizations, what are they doing, with the U.S. government, ECMWF, et cetera, to improve that assimilation? Is it a computing power problem, or is it something that just needs to be improved with the process to bring the data?
Okay, so it was in 2007. So this is the data for 2007, what I showed. And it did improve some. Actually, it did improve significantly. But it's probably still well below 10%, I would say. And there are a number of issues. I mean, there's a lot of redundancy in the data. That's one issue. Because especially these new instruments, which has thousands of channels, satellite channels, what you basically do, you subsample it. You take a few hundred channels and you just look at those.
Just an explanation, channel referring to different wavelengths of the spectrum.
Yes, but now we have instruments that can look at 4,000 different wavelengths, and some of that information is redundant. Another issue is just computing power. I mean, you have to touch this data, you have to quality control this data, and then you have to make a decision whether you would like to use that data, and then you have to assimilate the data. I mean, we are talking about huge matrices that you have to invert and so on. And there is a limitation to that. And there are some data we just don't know how to use because the radiative transfer models are not good. Because basically what the radiative transfer model does, it makes the connection between the observations that the satellites do and the state of the atmosphere. That's one of the big challenges with satellite-based observations, that you are not measuring temperature directly or CO2 concentration directly, right? You measure radiances, and then you have to come up with a good estimate of the state. But it's, and also there are politics. If you would ask some of the guys at the national, at the different data simulation centers, they would tell you that they didn't ask for certain satellites. It was the satellite lobby, and that's an argument you hear many times. But the goal is definitely to increase. And it did increase since that slide significantly.
If there are any statistics experts with a lot of time on their hands, data assimilation is a statistical problem, and the basic assumption that's typically made is that different observations are independent of each other. But with satellites in particular, you've got observations taken over adjoining space by the same instrument, so you have correlated errors, and how to deal with that in an optimal fashion is a big unsolved problem that could lead to a lot of progress.
So Conrad Lorenz was invoked several times tonight.
It's Edward Lorenz, it's not Conrad Lorenz. It's not the...
So the sensitivity to initial condition, and in particular, perhaps mostly to you, can you separate the sensitivity to initial conditions versus any physical forcing that might have occurred for where you're not getting the paleoclimate type?
I mean, this is probably the one type of experiment that we feel good about using climate models, in that we tend to like the variability that they do on their own. What I was showing that, you know, if you don't put any external forcings, we like what we see. It seems reasonable. What, you have a...
My point with regard to that comment would be you would have to do that experiment with different initial conditions, not just to look at the variability over the time span of the group.
Yeah, so in these experiments, if you change you know, the solar forcing by a microwatt, the whole experiment will be different. In some sense, it's the same as a different initial condition. And so any differences in these models, since you repeat, usually when you repeat these experiments, you do start with a different initial state and they play out. But I'm saying any change in the model that you make plays itself out, and you sample a different way that natural variability could express itself in time. And then so that's, in some sense, that's what these experiments are there to sort out, is how much is the force signal there above the natural variability. And little medieval warm period and little ice age are, in some sense, small signals relative, well, they're comparable, let's say comparable to the noise, but there's noticeable if you repeat the experiment again. Yes, yes.
But I think one thing that is important to point out, that these are two different types of predictions. What I'm talking about is predicting all details of the weather, when a certain cyclone will go through and when a cold front will go over Houston and so on. And what they are talking about climate. So if you just want to use an analog, I mean, I could talk about the temperature in this room, right? If you want to do it from first principles, you have to go and solve all the motions of the molecules. And that's what I'm trying to do when I'm predicting the weather. But you can predict the average energy of those particles, and that's the temperature. So, and that's what they try to do in climate, although I think they are realizing more and more time that climate is more sensitive to initial conditions than people typically thought before. People thought that that's really a statistical problem. It's more like statistical mechanics. And I think people found in the IPCC reports, they try to run the same models from different initial conditions, because there is a surprising sensitivity to initial conditions. But these are different type of predictions.
But presumably that sensitivity would also show up in the natural event, not just in the model, but in the natural event. That is basically what I was saying.
The observational data itself has, it's right. So you just don't look at the average model. You like to know the spread at any given time of the models, and that's kind of shown in the gray, in that one figure, that it includes the models, each individual model's interpretation of what happened at that time, and then there's an envelope.
And let me add that is that's probably the biggest problem with attempting to estimate climate sensitivity based on the observed record. Because with climate models, you know there's natural variability. You can run it several times and see what the force signal is. With the atmosphere, we only have one realization, one set of events that's taking place, and there's no objective way of cleanly separating out what was natural from what was forced. And so there's always that uncertainty. The longer it goes out, the more the natural part will even out, but in some sense we can't wait that long.
Right, so in the first approximation to the paleoclimate, you could take each Heinrich event as a different expression of an initial condition.
Yes. Let's see, how many more questions can we take?
Let's make 2 more questions.
All right. You and then you.
A lot of meteorological services are predicting for a colder than normal winter. based on El Niños and warm waters of the Gulf of Alaska, TDO. But you guys are telling me that you cannot believe anything past 3 weeks. Does it mean that they're not or should I take any weight on their forecast?
Oh, no. I mean, once again, these are two different types of predictions. So what I'm talking about is predicting the movement of the individual cyclones. What he's talking about, that what he says is when we have an El Nino, we will have more cyclones passing over California. We don't say anything about on which day, how many of them. We are saying that there will be more than typically we have. And we will have more rain because cyclones produce rain. So, and that's the type of, we are basically, when you lose the predictability, what I'm talking about, you are losing your capability of predicting the individual events. But it doesn't necessarily mean that you cannot say that, well, we will have more cyclones where you live. And it will be more wet and it will be colder because of that. It's a different type of prediction, far less details.
The one way to think about it is that if you have normal ocean temperatures, the globe has one distribution of climate. And if you have a different set of ocean temperatures, then the expected climate conditions are going to be slightly different. And so that's the difference that we're detecting with El Nino, which has a time scale of months, so we can say for these few months the climate is going to be perturbed in this way. But yet, on top of that, there's the range of possible weather events, which is broad enough that even these forecasts you say hear about a cold winter, if you actually look at the forecast itself, it's saying we've got a 60% chance of a cold winter, whereas normally you have a 50% chance. So the odds are only tilted slightly, and it's only when you get to, say, a really strong El Nino or La Nina that it's tilted so much that you can have a lot of comets that really will be cold or warm. And last question.
Well, one thing I've heard is that temperatures are not rising quite as quickly as the models have predicted, and that the energy is getting stored in the oceans. And I was wondering if someone could maybe explain a little bit of the difference between what we know in the atmosphere above land versus the temperatures of the ocean, and how that data is actually collected so we know what's happening in the oceans.
Okay. So since this was a talk on climate and weather modeling, I didn't talk about it. The issue you're raising is called a hiatus, that there's been a slowing down in the warming in the last 10 to 12 years. And the most likely candidate is the ocean absorbs some of the heat. There's some argument over whether it's the Pacific or the Atlantic and exact details by which it happened. Again, I mentioned one of the reasons people were looking for El Nino this year was to mitigate the drought in California. But there's another reason people were hoping for a huge El Nino is that it'll show that if you have a huge El Nino, the global mean temperatures go up they could go up by 0.5 degree within a year. So if you go without El Ninos for about 5 to 10 years, the global mean temperatures will drop, and if El Ninos come back, then they'll pick up again. So that's one way to think about it, is that there is clearly a hiatus. How much of it we can explain using ocean heat content, we don't know, or whether it's just fewer El Ninos happening, we don't know that yet.
Yeah, so to a general comment, if you take a look at Charles Jackson's slide of the unforced climate models, they're going like that, you can superimpose the trend. They're still doing that in top of the trend. So, but the projections that you get publicized from say IPCC models and so forth are the average of all of the models with the natural variability smoothed out. So none of that was part of the goal of the projections. And so in that sense, it wasn't forecast because nobody tried to forecast it. In another sense, it wasn't forecast because it wasn't possible to forecast it. In the most recent report, we have a chapter now trying to look at predicting over, say, a decade scale where the natural variability is more important than the forcing. And the present state of the art is you run different models from similar initial conditions and try to simulate the ocean where most of that stuff's taking place. It takes about 2 or 3 years before they're all giving different answers. So we got a ways to go with that, but in principle with more observations and better models, that's something that can be tackled, and that's probably where the biggest advance in forecasting is going to happen over the next decade. And with that, thank you very much for your attention.
I hope you enjoyed this as much as I did and getting a picture of what's going on with weather, climate, and our ability to model it. It sounds like we still have a long ways to go, but we've also made some very good strides. And so I'm looking forward to the future as to what these climatologists will be able to do in helping predict what's going to happen. So let's thank them again. And I want to say thank you for coming tonight. Again, if you enjoyed the program and you think you would like to be a sponsor or get involved with the MIT Enterprise Forum, we'd love to talk with you. So please see myself or any of the committee members here tonight. So with that, please drive carefully home.